Greetings and welcome to our presentation entitled Prescribed Time Closed-Loop Performance Assessment Comparative Case Study. My name is Ramon, and this work is co-authored with Dr. Yuri Orlov and Dr. Luis Aguilar from CCSE and IPN respectively.
The outline of this presentation is divided into 5 items, and I would like to start by the introduction. This work is motivated by critical convergence time applications like the working of a Viper robot and an inside intersection task. In both of them, we require that the control goal to be achieved in a small time window. Given the necessity of this kind of regulation in a certain amount of time, we will focus our study in prescribed time and fixed time output feedback controllers, and we will compare them in the context of output feedback stabilization in fixed time. To do so, we introduce 2 typical scenarios with a simple pendulum, the closed loop in the presence of external disturbances, and the closed loop in the presence of measurement noise. We will use indices to compare, and of course, relevant conclusions will be drawn from the collected simulation data.
Let us introduce a problem statement as follows. We have a second order system in 1, which is affected by matched disturbances W and measurement noise W sub 0. This system is described by the matrices capital lambda, capital B, and capital C. The assumption about this system is that the external disturbance W is uniformly bounded with an a priori known constant capital L. So the problem is to meet the prescribed upper bound capital T on the certain time function for the unperturbed closed loop trajectories independently of the initial states. To solve the problem previously mentioned, we review in this section 3 different fixed time stabilizing algorithms. The first one is the algorithm by Lopez Ramirez in 2018. This controller is defined with these parameters in 3, 4, 5. Once you select accordingly these parameters, you can introduce the output feedback controller presented here in 6, which is composed by the state feedback fed by the observer states, and also this observer state comes accompanied with this filter. The tuning parameters of this output feedback controller are presented in the right hand side of this slide, and once you take properly these parameters, you ensure that by theorem 4 in this citation 2, the disturbance-free closed-loop system is fixed time convergent with respect to the sets that I'm presenting here for any initial conditions. In addition, if its input stay practically stable in the sense of definition 2 for any disturbance W which is upper bounded by constant capital L, and measurement noise W in L infinity. The second controller is the one by Holloway and Krstic in 2019. This output feedback controller is presented in 10 and is fed by a state observer that I'm presenting here, where the injection terms of the observer are given here in 11. The synthesis of this output feedback controller 10-11 includes the use of this time varying gain mu1, which as we can see here, it's defined in the time interval 0 capital T and escapes to infinity as time approaches the final time capital T. Tuning parameters of this controller are the capital T, let's say the upper bound on certain time function, those loop trajectories, and these constants that should be selected as I'm showing here for this matrix, for instance, to be Hurwitz. If this condition is satisfied, then by theorem 1, the disturbance-free closed-loop system is fixed time stable with the prescribed convergent time capital T to the origin, irrespective of the initial states. In this case, output feedback controller is built from the state feedback presented in the American Control Conference and an observer presented in the European Journal of Control. The prescribed sampling time interval is divided into 2 sub-intervals. In the first interval, the observer will converge, and in the entire interval, it's expected to the closed loop trajectories to converge to the origin. In this slide, we are presenting the output feedback controller in 13, 14, and 15. together with its injection terms presented in 17 and 18. The tuning parameters are given here, where capital T1 is the upper bound on the setting time function for the observer, and capital T is the upper bound for the setting time function of the closed loop system. The result parameters are presented here and should be taken properly. If the data parameters are chosen accordingly, then by theorem 2 in reference 9 and theorem 2 in reference 10, the closed loop trajectory is converted to the origin in a time no greater than capital T, irrespective of the initial conditions and disturbance applied.
This section is devoted to the simulation results using the pendulum system, as I'm showing here in this figure, where the parameters are showing in this table. If we define the regulation error eta 1 and eta 2 as I'm presenting here, then the dynamics can be transformed into 21, where W is the signal disturbance. It's given in 22. If we take the torque input as in 23, the resulting system dynamics 24, it's consistent with the one needed for the application of the three previously reviewed controllers. The simulation setup is then in this slide, where the prescribed time capital T is set as 4 seconds. To ensure a proper comparison, the parameters are tuned in a way that the three controllers, which we are here defining with this notation, these three controllers must perform with a similar job defined in this equation, and then I'm showing that actually they are performing with a similar job in this figure. Furthermore, the input disturbance W, which is defined by this relation, satisfies that is upper bounded, given that the external input D is modeled at here, and as I'm showing also here in this figure. In this slide, I'm showing the time responses of the disturbance corroborated aerodynamics and control inputs in the left and the right, respectively. As you can see, the UPSTB controller achieved a better regulation accuracy, which is also accompanied with chattering in the control inputs and also in the velocity regulation error. This is a typical behavior of this continuous control action present in the UPSTB controller. Furthermore, the work dynamics developed by the UPSTB remains constant after a certain time, which is possible thanks to this regulation error precision, while the other two controllers show increased value in this time window, from 0 to 4 seconds. At the bottom of this slide, we are also showing a comparison using integral indices of the three controllers, where the non-autonomous controllers PT and UPSTB exhibit the higher transient regulation, position regulation error compared with the fixed time controller, which is an autonomous one. Also, this non-autonomous controller exhibits a lower steady state error, which is assessed by the eta index, and also higher energy consumption than the autonomous one, and this can be assessed by the QE index in this figure here. Now, in this case, we are going to repeat the simulations, but in this case, in the presence of measurement noise. So the output now is the regulation error plus this signal, which is modeled by this block in MATLAB. Is a uniform random number distributed in the interval that I'm showing here. In this case, the result shows that the PT control algorithms is more sensitive to measurement noise, given that the increased value of the high gain nearby the prescribed time, which makes the regulation error to diverge from the origin, while the other two algorithms UPSTB and FT remain bounded in this nearby the terminal time. Of course, in this case, the non-autonomous algorithm PT shows a work value that is divergent nearby the terminal time. And also in this, in the bottom, with the integral indices, we can see how the PT algorithm possesses the higher QE index as expected from this amplification of the measurement noise. On the other hand, the PT and the non-autonomous algorithm PT and the PSTB exhibit a higher steady-state error than the fixed time algorithm, while also showing high energy consumption compared to that of the FT. So some conclusions are in place, and the first conclusion is that under bounded external disturbances, the fixed time and prescribed time steer the pendulum to a neighborhood of the origin, while the UPSTB preserved the regulation accuracy, as we saw in these figures. The disturbance rejection provided by the UPSTB is, however, accompanied by the shattering generation and hence by the corresponding high energy consumption. Large initial states were shown to provoke higher initial response values of the FT controller and the PT compared to those of the UPSTB controller. In the steady state, the measurement noise is critical for the PT controller, while with regulation error diverging near T equal capital T, along with the control input growing unbounded. This is reduced in a high energy consumption. In the presence of measurement noise, both FT and UPSTB suffered from shattering. However, its magnitude was lower in the FT versus UPSTB, which is also traduced in a lower energy consumption for the FT with respect to UPSTB controller. Thank you very much. If you have any question, please be free to ask.